All right, we're going to go ahead and start 13.6 here. We're going to look at velocity and acceleration in polar coordinates. So if we look here and we go into polar coordinates, we can see that we have two main vectors that we're going to want to look at here. The first is the unit vector that's pointed in the direction that our radius vector is pointed. That's u sub r right there. And the second is the unit vector that's pointed in the direction that theta is increasing. So that's what we have when we look in polar coordinates, r and theta. So it makes sense that we want to look at vectors that are pointed in those two directions. And note that u sub r is simply the radius vector divided by its own magnitude right there, okay? And then so let's go ahead and take a look at what we can do with this. When a particle at point P r of theta moves along a curve in polar coordinate plane, we express its position, velocity, and acceleration in terms of the moving unit vectors. So these unit vectors we just came up on the other page. The first one is ur is the cosine plus sine, cosine in the I direction and sine in the j direction. Obviously that's going to get us pointed in the right direction. And then the other one is the negative sign in the I direction and cosine in the j direction, which will point us in the direction that theta is increasing. And so for example, like if you're looking at, if we're looking back here on this curve, right, if we make this into a triangle, this is our cosine theta, this is our sine theta, and so if we make that unit so it's a 1, so we're looking only at the unit vector, so back over here or something like that, where we have a unit vector here, then then this is just cosine theta and sine of theta, and when you add those two vectors together, you get that unit vector right there. If you were to then flip-flop this around such that you went negative sine theta in this direction, and then went cosine theta up in this direction, right, then you would get this vector right here, which is pointing in the direction it's increasing, and is unit vector theta, like that. These were unit vectors, okay? So that's what we're talking about when we do those here, and that's how they're defined here. So the unit vector UR points along the position vector, and so therefore this is important. We can say that our position vector r is just a scaled version of that unit vector, scaled by the magnitude of r, and the vector u theta points in the direction of increasing theta. All right, so let's take a look here. First thing we want to do is find what are the derivatives of these moving vectors. And so we have dur d theta, which is just going to be the derivative of the vector we saw on the previous page, which was cosine in the I direction, which we take the derivative and get negative sine. And it was sine in the j direction, so we took the derivative and get cosine. And then the same thing here for du theta d theta. We had negative sine, which became derivative is negative cosine, and we had then cosine, which became negative sine. And if you look at this, these two flip-flop. So the derivative of the radial unit vector is the angle unit vector, and the derivative of the angle unit vector is the negative of the radial unit vector. All right, so that works out kind of nicely. There's also a couple more little things I want to do here real quick. First, dur d theta is going to equal dur dt dt d theta, and that has to equal our u theta, which means that we can multiply that over and we get dur dt equals u theta times d theta dt, right? And remember, whenever we do a time derivative, we're just taking, we can just actually write that as a dot. So let me move this over here so I can give myself quite enough room here. Let's put that right there. Let me move this over a little bit because we're going to need these results here in a minute. And so we can write this as ur dot equals u theta theta dot. Okay, so just like that. And then we can do the other one similarly, du theta d theta is going to equal du theta dt dt d theta, and that has to equal negative unit vector in the r direction. And so then this becomes u theta dot equals, and then we take this, we take our dt d theta and it moves to the other side and becomes d theta dt, we get negative ur theta dot. Okay, so I know I skipped basically this step there in that second one, but that's okay. You should be able to get that. All right, so now using that, we can take a look at how we find the velocity vector. So the velocity vector is simply going to be r dot, which is the first time derivative of it. And as we saw here on this previous page, we can say r is the length of r in the direction of ur. So r ur. So we make that substitution. All right, so a step in here was d dt of r vector, and then we replaced it with r ur. Now you apply the product rule, so it's the derivative of r times ur plus r times the derivative of ur, and as we just found above, the derivative of ur is u theta theta dot. So we end up with r ur, and then this ur dot becomes r theta dot u. All right, so we have no time derivatives of our unit vectors there. And so this is a very useful result right there. Well, it tells us our radial part and our angle part. And then we go on and we can do a second derivative of this. So for the second derivative, it's a little longer, but we can go ahead and do the product rule on this first term. And so we do r dot becomes r double dot ur, and then plus the derivative r dot and then ur dot, right? And then we can do, we can do the product rule on this one, but there's three of them. So we have to do r dot theta dot u theta, and then r theta double dot u theta, and then r theta dot u theta dot. So we've done each one of those. And then we can start making our substitutions to get rid of any derivatives of those vectors. And so we've got r double dot ur, that stays the same. But here we have ur dot, which was u theta. Oops, carrying my r down. R dot u theta theta dot, plus here we have just the same thing, r dot theta dot u theta. Okay, put my little unit vector hats on there, sorry. Plus r theta double dot u theta with a hat. And then here we have u theta dot, which is this one right up here. We can say this is plus r theta dot, and then times negative ur theta dot. And then if we go through and we start combining all of our like terms, so we have our ur vectors, that's this one and this one, so it'll equal r double dot and then minus r, right, we have this r and then a theta dot, so theta dot squared, and then that whole thing is in the ur direction. And then we've got plus, and now we have all these three to combine together here, right? We've got these. Well, this is r dot theta dot, this is r dot theta dot. So those two we can combine into a 2, and this one's by itself, it's r theta double dot. So this becomes r theta double dot, and then the other two combine to make 2r dot theta dot, like that, and those are in the u theta direction, like that. And then that's the result that we have right there from it. Okay? And so we derive both of those. Now, those are kind of a pain to derive, so I wouldn't recommend you really wanting to go through deriving those each time. based off of the definitions, but there it is. You've seen it once. Most likely you'll just want to kind of look those results up and use them when you need to. All right, continuing on here, you can see a picture of it. R dot UR dot right there. We've got that right there, and then we have R theta dot U theta. So those are our equations for this from back over here, where we had the R dot UR right there. Sorry, I guess you can't see me pointing at it. The R dot UR right there, and then the R theta dot U theta is that one right there. Okay, I don't want to leave all those circles on there, so let me get rid of those. Okay, and in polar coordinates, then the velocity vector just becomes the sum of those two, because those are defining our directions of motion. Okay, so add those two together, there's our velocity vector, which is what we got over here. All right, so here is find the velocity and acceleration of the vectors in terms of UR and U theta. So you're going to go through and just do what we had been doing over here, which is just going through and giving that a try. So we need to have, to do this, oops, sorry, going too far. We want UR and U theta, and so to find the velocity, it's jumping all over the place here. To find this velocity vector, we're going to do this right here. So we need R dot, and we need an R dot and a theta dot, and we have d theta dt is 2t. So R dot is going to be a time derivative of that, right? So this is dr dt, which is going to be dr d theta times d theta dt, like that. And so dr d theta is 2a cosine 2 theta, and d theta dt we were told is just 2t. And then we've got that right there. And so from there you continue on and just finish up the problem now that you have R dot, and do an R double dot, and so on and so forth. So I'm going to leave the rest of that for you to try. If you need to look in the notes and see how it's completed, I'll finish it off here for you. But for right now, we're going to go ahead and move on. But I'm just getting you started on that one. Try and finish that on your own, and then take a look at what I did to compare. All right, over here, we're just looking at position vectors and the basic unit functions in cylindrical coordinates, where we have basically a radius and an angle, and then also a height. And so you can end up drawing out a cylinder in the coordinates with an angle, a radius, and then a height, right, like that. So you're going out angle to a certain angle, like a polar coordinate, and then moving up a certain height in the z direction, like that. And so we can map out points on a cylinder. To extend the equations we just came up with to this, we simply add on that z component. So we add on a zk plus z dot k plus z double dot k, just like that. And so then that'll tell us it's these things motions in space. Okay, so taking a look at this, we have planets, some examples here. We have planets move in planes, so we don't have to worry about that z component. But we have Newton's law of gravitation, says that if r is the radius vector from the center of the sun of mass m to the center of a planet of mass m, then the force vector is the gravitational force. And it's written right here for you. Negative g m1 m2, or mass of the planet, mass of the sun, divided by the radius squared, and it's in the unit vector radial direction. So sometimes you might even see this written as negative g m over r cubed, and then r unit hat vector, like that. But anyway, it's just the force that is in between the two of them, and it is in that radial direction, causing them to go around in ellipses. All right, here you can see that a planet obeys its Newton's law of second gravitation, and therefore travels in the plane through the sun's center of mass and perpendicular to our cross product of our position vector and our velocity vector there, r dot. So that's what we have there. You put a plane there, and the planet goes to that plane. Most of the planets all travel in pretty much the same plane, and so we're all pretty much in line. I think Pluto, if you still count it as a planet, is the only one that really goes outside of that of our solar plane there. It's kind of, it has its own plane, but the other ones all pretty much in the same plane. Here we have Kepler's laws. The first law states that a planet follows a path around the sun, and it's an elliptical path, and the sun is at one focus. The second law, which is depicted here, I mean, you see this here. Actually, the first law is here. Here's that, and here would be the other focus. And so the planet goes around both of them while the sun sits at one of the focus. The other one, the second law, is also a statement of what is called conservation of angular momentum. And this is the idea, if you have the idea of conservation of angular momentum, it'll give you the second law. And if you have the second law, then it tells you conservation of angular momentum. So I don't know which one is more fundamental because they each give you the other. And so what this says here was Kepler's law was he noted that if you watch a planet move for a certain period of time, so like say we started here and then we waited 2 months until the planet reached over here, and we looked at like the pizza slice area that was in there, that filled in area there, and then we took any other place in the orbit over the same period of time. So say this was 2 months, right? And we waited over here, and this was 2 months. These two areas that are swept out will be equal. So if this is like area 1 and this is area 2, it's telling us they equal each other. One is long and skinny, and the other is short and fat. But those two areas are going to be the same. And what this tells you, excuse me, is that when the planet is closer to the sun, it's actually traveling faster. So it'll travel a longer distance around the sun, right? This length right there is longer, but it's closer to the sun, and so it speeds up. And as it gets further from the sun, it slows down, and so it doesn't cover as long of a distance, but the area swept out, sometimes called the aerial distance, the aerial velocity, the two aerial velocities, it remains a constant. It's always the same. And again, that just means conservation of angular momentum. Look at a figure skater. If they throw their arms out wide, they spin slowly. If they tuck their arms in, they start spinning fast. If the planet gets close to the sun, it starts orbiting quickly. If it gets further away, it orbits more slowly. And then the two aerial velocities remain equal or constant. All right, and this is also true anywhere else. If we picked some other place in between, like here and here, we'd have something in between, and this could be like A3, and this would also still equal. So as long as it's 2 months, they're going to stay equal, right? All those areas. Or really, just to clarify, it doesn't have to be 2 months. It could be 1 month or 1 day or 1 second or anything like that. It's all going to be the same. Here is Kepler's third law, kind of. Technically, this is the result from Newton's universal law of gravitation. Kepler's third law simply states that the orbital period squared is proportional to the distance it is, or the orbits the semi-major axis cubed. Okay, it's proportional to that. So basically half of the major axis there, or the average distance from the planet is from the sun. So the orbital period is the amount of time it takes for it to complete one orbit, and then A is from like the center between the foci out like that. That's our A right there. Okay, and so that's A. And that right there says that those two are proportional like this, and then Newton came along and he did this with his universal law of gravity and showed that it was true. All right, that t squared over a cubed equals a constant, because 4 is a constant, pi is a constant, g is the gravitational constant, and the mass of the sun is basically a constant as well. So it's those two things equal to each other, which means they are proportional to each other. So he kind of came along and Newton had laws, and then, Kepler had laws, and Newton came along and basically explained why those laws were laws with his universal law of gravity. Okay, here, just some pictures showing some more tangent vectors and things like that in these situations. But that's pretty much just it for this section. So if you have any questions on this, be sure to let me know. Otherwise, I'll see you next time. And that's the end of this chapter. Thanks a lot.